Good day to you. Today we're going to go over the chain rule for functions of several variables. So it's kind of an extension of the chain rule that you know from single variable calculus, which is, it may come in handy now and then. We're not going to spend a huge amount of time on it, but I want to make sure to formally explain it to you. Okay, so the chain rule says you have some function z equals f of x and y. It's a differentiable function of x and y. And if x is actually a function of t, say g of t, and y is a function h of t, if they're both differentiable functions of t, then you could actually write z as a function of t, and rather than just plugging in the g of t and the h of t in place of all the x's and y's, you can use a chain rule. The chain rule says dz dt, that's not the partial derivative, that's the derivative with respect to t. dz dt is the partial of f with respect to x times dx dt. That's the derivative of x, plus partial f with respect to y times dy dt. So you have a mix of partial derivatives and derivatives here. Because remember, f is a function of x and y, whereas x is just a function of t, y is just a function of t. Okay, so this is what the chain rule would look like for this function to take the derivative of z with respect to t. Okay, so take this example. Z is x squared plus 3xy to the fourth. And x is then defined as sine of 2t, and y is the cosine of t. So what we're going to do is use the chain rule then to find dz dt. So we're going to find the partial of z. I can write it like this. It's zx times x prime plus zy times y prime. This is another way you could express this using other notation. So the partial of z with respect to x is going to be 2x for the first term, and then we're going to have plus 3y to the fourth. And the derivative of x with respect to t, well, the derivative of x is going to be the cosine of 2t with a 2 coming out front because of the chain rule for functions of one variable. Now the partial derivative of z with respect to y, the first term is going to be 0 because it's constant with respect to y, and then we're going to get 3 times 4 is a 12, xy to the third, and then the derivative of y is negative sine of t. And so if I wanted to, for example, get dz dt when t is equal to 0, for example, x of 0 is the sine of 0, which is 0. Y of 0 is 1. So plugging all of that in, we're going to have 0 plus 3 times 2. The cosine of 0 is 1, plus 0, because the x there is x is 0, minus 0, 0. Yeah, the sine of the sine of t is 0. Yeah, the sine of 0 is 0. So in the end, we have 3 times 2. This is just comes out to be 6. Okay. Okay, so let's take a physics example. The pressure, capital P, that's in kilopascals, and the volume V in liters, and the temperature, capital T, that's in kelvins, of a mole of ideal gas are related by this equation, PV equals 8.31 T. Okay, so at what rate is the pressure going to be changing when the temperature is at 300 Kelvin, increasing at 0.1 Kelvin per second, and the volume is 100 liters, increasing at 0.3 liters per second? So if we're going to have to first off figure out what is the value of P, but we're going to, and that's going to be related through the equation, right? So P, we can write P equals 8.31 times the 300 Kelvin divided by the 100 in volume, and that's 24.93 kilopascals. I think that's the units, but I'm not going to be too hard on myself if I'm wrong. Okay, so now we want to take the derivative of this equation. Now I actually am going to write the p rather than using implicit differentiation or something. I'll just write p equals 8.31 times t over v, and we're going to take the derivative, get the partial derivative, dp dt. Now that's going to be using the chain rule. It's going to be the derivative with respect to t first, so it's going to be 8.31 over v times dt dt plus it's going to be negative 8.31 t over v squared. That's the derivative, partial derivative with respect to v, times dv dt. Okay, now we have the rate of change for temperature and the rate of change for volume, so we can plug these things in. So it's 8.31 over 100 liters times the rate of change for the temperature, and that is at that's 0.1, plus negative 8.31 times 300 degrees Kelvin, it's very hot, over 100 squared times 0.3. That's the rate of change of the volume. That's in liters per second. Okay, and this is going to be a rate of change of negative. It's a decrease of 0.06648 kilopascals per second. Again, I think that's kp is kilopascals. I assume it is. Okay. Okay, so now let's we're going to expand the chain rule a little bit. So suppose the same setup, that z is a function of x and y. It's differentiable, function of x and y, and x is not a function of just t, but it's a function of s and t, two variables. Y is also a function of s and t, and both differentiable functions. So now we can look at the partial derivative of z with respect to s, for example. That's going to follow a chain rule that's going to actually be quite similar looking, but in this case we're going to be having partial derivatives all the way through. So it's going to be the partial derivative of z with respect to x times the partial of x with respect to s. And the partial derivative of z with respect to t is going to be the partial derivative, plus the partial derivative of z with respect to y times the partial derivative of y with respect to s. And the partial derivative of z with respect to t is similarly going to be the partial derivative of z with respect to x times the partial derivative of x with respect to t now, and plus the partial of z with respect to y times the partial of y with respect to t this time. So you can see this is not too different, but this is just how this chain rule builds up with more variables, and you can look it up if you have a function of 3 or more variables and it gets even hairier. It extends in this similar kind of a pattern. You can check it out and see if you're not sure. So let's take this example. We have z is a function e to the x times sine y. X is actually s times t squared, and y is s squared t. Now, I want to find the partial derivative of z with respect to s, which, as I said, it's the partial of z with respect to x times the partial of x with respect to s, plus the partial z with respect to y times the partial y with respect to s. So these are going to be, well, it's the derivative of e to the x is e to the x, so it's e to the x sine y times the derivative of x with respect to s, which is going to be t squared. Now the partial of z with respect to y is going to be e to the x cosine of y, and the partial of y with respect to s is going to be 2st. And I'm not so interested in cleaning that up any further. For this example, let's just get the partial of z with respect to t now. So again, the formula partial z with respect to x times partial x with respect to t plus the partial z with respect to y times partial of y with respect to t. Incidentally, if you wanted to, you could write something like zx equals, it would be zt equals zx xt, right, plus zy yt. This would be the shorthand that you could use with partial derivative notation, if you like that sort of thing. Anyway, the derivative of the partial with z with respect to x is actually the same as the line just above, so I can just copy that over. Now the derivative of x with respect to t is going to be 2st. And the partial of z with respect to y is e to the x cosine y. And then we have the derivative of y with respect to t, which is y with respect to t. It's going to be 2. Oh no, it's just s squared. Now, if you wanted to, you can take this and you can plug in st squared in place of the x's. You could plug in s squared t in place of the y's, but I am not going to do that. But I'm just saying you could. This is a fine form to have your answer in. Even though you still have x's and y's involved, you can evaluate that certainly for any value that you care about. Well, that's all I want to say about the chain rule for functions of several variables. And we will not really be doing so much with this in class, but I just want you to know about it. Maybe we will do something more about it in class in the future, so don't take that to the bank. Alrighty, bye.